Hello. In this video, let's talk about first the functions of building elements. Let's review them from our last video, and then we can move on to building structure and what kind of materials that we can prefer in order to construct the structure. We can take a closer look to concrete and reinforced concrete. We can learn how we can create reinforced concrete columns, shear walls, and beams, and floors as well. We can start with this question. How do we provide a healthy and comfortable living environment? We should remember that that's the job of building elements, and we need to remember that each building element can execute a certain function. We can have this example. It's a very nice design made by Gray Organji Architecture. It's an ecological living module, a detachable, small, tiny building which can serve for a user to live a healthy and comfortable life without depending the outside factors such as electricity or water, because the whole building has been designed in order to provide everything a person may need in order to survive their lives, including the food. It's a very small building. As you can see here, there is this semi-open space, a terrace area, and the sloping roof surface. There is this side door or window we can call, and in the opposite wall, you can grow your vegetables. There can be some edible plants that you can provide for food. On the roof, we see some solar panels, so the you can produce electricity. Also, there are some systems at the back which helps you to collect rainwater, to purify it, and recycle the gray water. There is this compost toilet. And necessary equipment for all these systems. Uh, the architecture firm, they provided some very nice diagrams. So when we take a look at these drawings or perspectives, we can understand how the building has been designed, what kind of spaces it holds. Here, this is the semi-open space, the terrace area, and when you step inside, you can find a table, a foldable table, which you can either use for eating something or for working. And there's the sofa that you can relax on. Here you can prepare your meals. That's a small kitchen area. And behind this surface, the door, there is the shower and toilet space. And there is a semi-floor, mezzanine floor, we can call it, and it's for sleeping. Some inside photos, uh, very nice indoor area. So you remember that we talked about building products, and we can examine them in 5 levels. The first is the building itself, the whole building. So the architect, they designed a mass in this geometrical shape, and it can provide these units, which are either closed, semi-closed, or open living areas, which can have certain functions like sleeping, like preparing meal, like eating, uh, like that. So all these units and all these living areas can be created with the help of elements. You remember that a building element is an integral product, and we can form it either combining the materials or pieces or components so that uh, the functions that needs to be provided by the building can be executed, and each one of these elements have can manage either one or more than one function. The main function of the building is to provide protection from all the negative features. So when we take a look at this building, that surface is a wall, is one of its elements. And that one is a roof, another element. And they can help with the protection. Uh, Imagine that it's the winter time and it's raining outside, and we don't want our user to get wet, our indoor environment and furnitures to get wet. So there comes the roof. If we design a good roof and accurate, if we make accurate decisions for this building element, then it will prevent the rainwater to build up in the indoor environment and cause problems. That's one of the functions that are executed by the roof element. According to our decisions, we can add some more functions like producing electricity if we prefer these solar panels. Uh, Another example, it's cold outside, we want a warm environment, and we know that heat is transferred through the warm space to the cold space through objects, physical objects. But if we design a good element, then that element, that roof and the walls, they can prevent heat transfer. They can work for protecting the heat in the indoor environment. Uh, Another building element, stairs. It functions for our user to move between different levels so that they can reach in this sleeping space. Floors, another element. So all these elements, when they gather up with our decisions, according to our decisions, they will provide nice living spaces, building units, and then nice built environment for the user. But we need to remember that we are placing window panels, roofing materials, solar panels, and everything. And because of the gravity, they have weights. And all these things make uh, cause certain loads on the building, and we don't want them to fall down. We don't want the building to collapse down, break into pieces. How do we keep the building intact in the form that we want against all these loads? Here, we need building structure. That's one of our elements, and we need to learn with what kind of materials that we can construct a building structure. Uh, there can be vertical loads uh, directed towards the surface of the earth because of the gravity, or there can be lateral or horizontal loads. Each one of these building pieces, the panels, the roof covering, or the birds that fly over the building and they land on the roof. Even us, our furniture, because of the gravity, uh, uh, we cause vertical loads on the building. Blowing wind may create this lateral load, horizontal load. Same with the earthquake. When the earth moves, it causes the building to move laterally. It forces the building to move laterally. And those are what we call lateral loads. There is a very nice video here. Let's take a look at it. And we understand that the effects of earthquake depends on the properties of the earthquake and properties of the building that we designed, including its height and including its form. Let's take a look.
Slowly back and forth, I can get the tall building to oscillate where the intermediate and short buildings are not moving. If I move it more briskly, I can dial in the rate of horizontal oscillation so that I move the center building, the intermediate height building, and the short and the tall ones are barely moving. To get the short building to oscillate, you need to move the base very briskly back and forth.
So all these loads, the weight of the furniture, weight of the users, either vertical loads or lateral loads, they need to be met, they need to be carried and transferred safely with a building structure. That's the element itself. Structure helps us to keep the whole building form in this three-dimensional shape without collapsing down. And it it's executed by meeting and carrying and transferring all the loads safely to the ground. So that's how we need to think when we are designing, making decisions about the building structure. What kind of form are we do we want to have? And in order to keep that form intact, what kind of a structure we need to design, and what are the possible loads that can act upon the building, so that we can make these decisions about the structure according to the form and all the possible loads and their properties. Uh, but with what kind of components we need in order to create the element? We have two main components, as you remember. These vertical ones are called columns or studs, and the horizontal ones, they are beams. Uh, and we need to remember that load transfers hierarchically. First, the surface of the roof or the surface of the floor, they get all the loads, and they transfer this surface transfers its loads to the sides, to the beams. And each beam, they get the loads and they transfer it to the columns, and it goes downwards where we find the ground. Um, let's take a look at this uh, video. If we manage to have components in right sizes, if we prefer good materials, strong materials, and if we connect them uh, properly, then the building structure will meet all the loads, carry them, and transfer them so that the whole form of the building will be intact. Otherwise, there is this risk of collapsing down, breaking into pieces, which we call deformation. If the vertical and the horizontal components are not strong enough, they will break into pieces under the loads, like this. So let's take a look at the materials. If you want beams as the components, if you want columns as the components, with what kind of materials can we create them out? Uh, First, there is wood. That's a trunk of a tree, and the type of the tree, that's important. We know that some trees, they provide soft wood, and they can be vulnerable against all these outside conditions like humidity or water or insects. But some trees, they provide very hard, very strong, very durable woods. So for the structural components, we need those type of trees. And when we cut them into pieces, when we saw them, we will get these shaped dimension numbers. That's what we call kerestet in Turkish. Uh, these are the shaped pieces. And that middle part, maybe according to the sizes and properties, can be used as a column, as a component. And that part maybe can be used as a beam with its shape. Uh, that's what we call a timber structure. All the components, columns, and beams are made out of timber. Instead, you can prefer these shapes made out of steel. As you know, steel is made with iron, and iron is a metal. And metals, we need to extract them from the earth in these rocks. They look like rocks, stones, but they are not. There are metal atoms inside this formation, and we need to extract them by mining the ores. And we need to convert them into a definite geometrical shape. And we can prefer these profiles for the studs, columns, and we can connect these studs, these vertical columns with horizontal beams made out of steel. Or we can prefer reinforced concrete, which includes concrete and steel reinforcement bars. When we combine them together, we will have reinforced concrete. And it looks like this. We don't see the steel bars because they are embedded inside the concrete, and we just see the surface, this gray surface for the columns and the beams, uh, which is concrete. Uh, so let's take a look at the properties of reinforced concrete. What is reinforced concrete and why do we prefer it so much for the building structure? First, we need to understand what concrete is. Concrete is a mixture. In Turkish, we call beton. It's the French pronunciation or French word uh, that we use in Turkish. And it's a mixture. It's a mixture of cement, that gray powder, and it's çimento in Turkish. We need to mix it with sand, kum, and gravel, that's çakıl, tiny stones, crushed stones. We can provide them either from nature in these small forms, or we can crush them in factories. We take bigger rocks and stones, and we create these smaller rock pieces, stone pieces, which we call gravel, and it can be made out of granite or different natural stones. That's we call aggregates. Sand and gravel, they are aggregates. Aggregate means filling, filling. Agrega in Turkish or dolgu, filling. That's we use these aggregates, sand and gravel. They are used in order to fill the gaps between cement particles. Since cement is a very expensive material, when we mix it with sand and gravel in order to fill all these gaps, it means that we can decrease the amount of cement, decrease the costs, and those gravel pieces, sand, they provide a very strong material, especially for the loads, pressure loads. And of course, we need water. We need to mix all these ingredients. And when we do that, cement starts to react. And first, a sort of paste, a semi-liquid, semi-solid paste is formed. And in time, it starts to get hard. It solidifies and turns into this solid substance, which we call concrete. Cement, it's this grayish powder, uh, and it's made out of limestone. First, we find limestone from nature. We extract it, and that's kireç taşı, a certain type of natural stone, and we need clay, kil, toprak, earth, and we need to pulverize them and mix them together, and we need to burn them in kilns, very big ovens. We need to heat them up to 1450 centigrade Celsius, and they start a kind of chemical reaction altogether, and these tiny grayish rounded particles are created, which we call clinker. Uh, Same in Turkish. And we need to pulverize them one more time. We need to grind them into dust, and we need to mix them with some gypsum so that we will have this cement. Uh, and it's ready to use. We can store them in silos. These are spatial storage buildings or equipment, let's say. And they are provided in these 50 kilogram bags, paper bags. Uh, and when we mix the cement with aggregates and with water, uh, this semi-liquid paste that we call green concrete uh, is being formed. And that material, concrete, is a cohesive material. Cohesive means the molecules of the substance, the molecules, different molecules of the concrete, they have uh, an ability to stick to each other very strongly. So each different concrete molecule can stick to its neighbor in a very strong bond. That's cohesion. And as the cohesion increases, the fluidity of the material decreases. As you can see, if there are little cohesion between different molecules of the concrete or the substance itself, it becomes very fluid. But as the cohesiveness increases, the fluidity decreases. Also, concrete is an adhesive material. Cohesive and adhesive, these are they like very similar, but there is this difference. Cohesion is the strong bond between the same type of molecules of the substance. However, when we are talking about adhesion, the molecules of the substance, in this example, the molecules of the concrete has this ability to form very strong bonds with the molecules of other substances, not the concrete, but some other substances, uh, like the aggregates or like the steel reinforcement bars. Uh, the aggregates, the either sand, fine aggregate, or coarse aggregate, the gravel, uh, they are made out of, both of them are made out of stones and rocks. With the help of cement, they will be binded together. Because cement is an adhesive material, it has this ability to form strong bonds between different particles of the sand and different particles of the gravel. That's why we call it a binding material, bağlayıcı, because it binds all these different particles of sand and gravel into one solid object, like that. And that's why we call the concrete as an artificial stone, because that's what we create, yapay taş. We create some sort of stone in the factory. When we mix water with cement powder, a reaction which we call hydration or hidrasyon in Turkish, uh, starts, uh, in which the grains of cement, the particles of cement, they start to dissolve and they form these strong bonds. They change their shape. Here we see these black grains of cement and gaps in between them. They are separate particles, but when we add water, they start to dissolve and create these bonds. So they became unified, wholesome. There's a video. Let's take a look at that video.
Cement powder and water react and harden through a process known as hydration. During hydration, the cement grains enter into contact with water and they begin to form a strong rods network structure, which is responsible for the final strength of concrete.
Since at the beginning it's half fluid, half solid, and it's not strong enough to hold a form, we need molds, kalıp in Turkish. Uh, and we need to pour the concrete into these molds. The molds will provide its final shape. So we need molds that with what kind of shape we are aiming for. And we let the concrete to stay in these molds so that it can set. Setting means changing its physical properties. In Turkish, we call it priz almak, priz almak. As you can see, at first, it doesn't have a definite geometrical shape. That's where the molds come into play because it's plastic. If we apply forces, it won't be able to hold that load. It will be deformed. So we need time for the concrete to set. Uh, let's imagine that's a timeline, and that's where we put the concrete into molds and where the setting starts. And it will require a certain amount of time. As the set starts, the half liquid state starts to turn into fully uh, solid state. It begins to harden. The physical state changes. Uh, and that's the point, the starting point is called the initial set. So after this time, after this moment, it starts to get hardened. And if we provide enough time, at the end, the set will be completed. That's what we call the moment we call the final set. And it's a fully hardened object. It's solid now. But it's not strong enough to hold loads. It's fully hardened, it's solid, but at this moment, it's not hard enough to carry the load. So we let a little bit more time so that it gains strength, sertlik kazanmak. So that when the loads are applied, either compression loads or shear loads or other types of loads, the stress will not be exceeded and it won't be deformed. We need to wait a little bit more here. Uh, This is how we can understand it in a better way. If we want to create that form, that rectangular prism out of concrete, first of all, of course, we need molds. But before the initial set, before the setting starts, we need to place the concrete, the green concrete, into the molds. Uh, and if we are late for placement, if this moment has passed, it won't be good to place the green concrete into the molds because it already starts to harden and the concrete will not fill all the form so that there will be some problems with the form, with the shape. So we need to place the concrete before the initial set, not after the initial set, before the initial set. Because once it passes this period, this moment, since it starts to be solidified, the form will not be what we want it to be. And we need to keep the concrete inside this mold after the final set. We shouldn't remove the molds before the final set happens. But after, if it pass this moment, then we can easily remove it because it's a fully solid object. But we shouldn't apply, we can remove the molds because it's solid enough to hold its form, but we shouldn't apply any loads and we need to wait a little bit more so that with the loads applied, it's hard enough to carry, and transfer all these loads. If we hurry to apply the loads right after the final set, it can be deformed since it's solid, but it's not strong enough. So we need extra time so that it will uh, gain some strength to carry all these loads. That's concrete. But what's the difference between reinforced concrete and concrete? And it's the steel reinforcement bars. Uh, with the reinforcement bars, which we call donatı, and these are rods made out of steel with different diameters and different shapes. Uh, the concrete becomes more stronger, and reinforced concrete is not the same material with concrete. For reinforcement bars, we can either prefer these plain ones, but it's not good. As you remember, we want concrete to adhere strongly on the surface of these rods. So instead of plain ones, we should always prefer these deformed ones. In Turkish, we call them nervürlü donatı, so that all these bumps and grooves they increase the surface area and concrete can have more space, more area to adhere in a better way. Uh, Concrete is produced in concrete plants. In Turkish, it's called beton santrali, and they can be provided from these factories, so to say. Uh, and uh, it needs to be mixed well with the aggregates and water, the amounts, they are important, and the mixture properties, it's important. We can do the mixing job on site with a hand mixer like that, but it's not very good. So instead, we can provide the already mixed concrete and we can transport them with these transmixers. Uh, in factory, it will be better mixed with very finely adjust amounts. And from factory to the construction site, we can transport all these concrete with these transmixers. You know that this part rotates during the travel, and inside that there are some spiral blades alongside the road. The blades they turn inside towards the inside center of the trunk, so that it keeps mixing. But when we arrive on the construction site, the rotation is now opposite. So all these blades, they force the concrete outside to pouring. Uh, and we need to pour it into molds, beton dökmek. That's what we call it in Turkish. And as you see, before the pouring, the builders, they arrange, they lay all these reinforcement bars, and the concrete is poured on them. So they will be covered, embedded inside this concrete because as steel it's prone to rust, to be rusted, uh, and that's something that we don't want. We need this. We need to keep it inside the concrete so it won't get corroded. Uh, and we can use pumps, concrete pumps, to reach longer distances or upper floors. That's a device, a machine which can be attached to the end of this transmixer. So poured concrete can be forced alongside of these holes with the force of the machine. And we see that these molds, they can be in different shapes. The voids will be filled with concrete. So whenever the molds are removed, we will have this in final form, final shape. So we need these molds, and they can be created out of timber material or steel or plastic. The important thing with the molds is they need to be reused over and over again. As you can see, first they place these molds here on this story in order to create these columns. And once they are set enough, once the final set is over, they are removed, the molds are removed, they are carried to the upstairs to create these new columns and then over and over again. So they need to be strong enough, durable enough to be reused over and over again. And we need scaffolding. That's what we call iskele. These temporary supports, tiny columns or studs, you can say, to hold these forms in their place. And they shouldn't be removed uh, uh, as before the concrete is strong enough. Uh, they should be removed after the final set occurs and some time has passed. Otherwise, it won't be able to hold all the weights of these reinforcement bars and concrete and workers and everything. So we provide the scaffolding, and over that we provide the molds. We place the reinforcement bars in this grid. We tie them together, and we pour concrete. We want the concrete to fill all the gaps between the reinforcement bars and all the void of the mold, so that when we remove the molds, we will have this final shape. Like that. And we need scaffolding to hold, to carry all these loads, so that after the final set, we can remove the scaffolding. This is something we need to avoid. And we want to concrete to fill all the gaps. And since since the concrete has this aggregates which can include larger coarse particles, uh, and there can be some tiny gaps between these reinforcement bars. Sometimes it can be hard for concrete to fill all the gaps. So we need to vibrate the whole concrete by using these electrical devices. We put the metal end inside the concrete, and we run the machine, so it creates this vibration. And with this vibration, the whole placement can be in a perfect way. Otherwise, without the vibration, without the uh, this device, there can be some gaps where coarse particles are stuck between the steel rods, reinforcement bars, and we don't want that at the end. Uh, it's both unstable because these are the weak parts. It won't hold under the pressure, under the loads. Also, we don't want our steel bars to be open to the air and humidity, so that they will be corroded. That's something that we need to avoid. How can we construct these components, these columns and beams out of reinforced concrete? First, let's take a look at the columns. Uh, for that, we need molds in the shape of the column that we want. That can be a square shaped or a rectangular shape or a cylindrical shaped column. And we need reinforcement bars. First, we do this reinforcement, and then it's surrounded with molds. And then we pour the concrete from the top, and we vibrate the whole concrete so that it reaches all the gaps towards the bottom, and everything everywhere will be filled with concrete. There's this video, you can take a look. As you can see, these reinforcement bars, they are tied together strongly, and then we place the molds. We close the system. Molds should be supported because of the pump. It pushes the concrete so hard, so we don't want our molds to be uh, collapsing down. So we tie them strongly, and we provide these supports. The upper part is open, of course, for us to pour concrete. These are some diagonal supports. And now we start to fill the concrete. We vibrate it, and as soon as the final set is over, we remove the mold. As you can see, mm, yeah, we won't be able to see the reinforcement bars here inside the concrete. And when we take a section horizontal section, that's what we are going to be seeing. There are different reinforcement bars in the column. Uh, these are vertical ones. Here, you can see them on the plan. Vertical reinforcement bars, düşey donatı. And they are connected to each other with these horizontal or lateral reinforcement bars, which we call etriye. Etriye. And everything needs to be embedded in the concrete, and there needs to be a thickness outside the lateral bars so that the steel reinforcement bars will be embedded inside the concrete. They won't be in connection with the outside air, outside water, humidity, and everything. That's what we call a concrete cover, the thickness of concrete. In Turkish, it's paspayı. And if we want, we can have these spiral or cylindrical columns. Again, we see a similar type of vertical reinforcement bars here inside, but instead of lateral bars, we have this time these spiral reinforcement bars, which we call thread in Turkish. And there needs to be a concrete cover uh, like that. Uh, and there are some rules that we need to follow. We need to obey if we want our structure to be strong enough against different types of loads. Uh, and Ah, before that, sorry. How do we create that concrete cover? We need the reinforcement bars not to touch the inner surface of the mold, so we can use these plastic substances so that there will be a distance between the inside surface of the mold and the reinforcement bar. And when we pour the concrete, when we fill all this gap with the concrete and remove the molds, we will have a nice concrete cover. If you want our structure to be strong enough against lateral loads or vertical loads, the sizes of the column, that's very important, alongside its material. A reinforced concrete column cannot be smaller than 25 centimeters to 30 centimeters in the plan. And here, this side can be minimum 25 centimeters, and that side can be minimum 30 centimeters. That's the minimum size for a reinforced concrete column, according to the regulations in Turkey. Uh, it shouldn't be smaller than that. And this whole surface here cannot be smaller than 750 square centimeters. And there needs to be at least 4 centimeter thickness for the concrete cover. That's the minimum for the protection of the uh, reinforcement bars. Uh, and we have another type of vertical component, which we call not a column. That's a column. You can think it as a longer column, a very long column, like a wall, which we call shear walls. And they work like the columns, exactly like the columns. Again, they have these reinforcement bars, and it's made out of reinforced concrete. The whole wall surface is made out of reinforced concrete, and they work to carry the vertical loads. And if you want to create a shear wall, that's perde duvar in Turkish. I forgot to write I realized that I forgot to write the name here, so I will write it here. Perde duvar in Turkish. A shear wall cannot be thinner than 20 centimeters in plan. Here, that distance we are talking about, that cannot be thinner than 20 centimeters, this thickness. And it needs to be proportional to the height of the wall. As the wall gets higher, then it needs to get thicker as well. And we can find the minimum thickness by dividing the height of the wall, the total height of the wall, into 20. That's our minimum thickness that we need to provide. Uh, okay, now we can move on to reinforced concrete beams. Let's take a look at how we can create the beams. The same principles. Again, we have reinforcement bars. It's all embedded in the concrete. The only difference is these are horizontal, not vertical, but horizontal. And there can be, again, some minimum sizes that we need to follow. The thickness of a reinforced concrete beam, this size, cannot be smaller than 25 centimeters. And the height of the beam, that size, cannot be smaller than 30 centimeters. As you realize, it's same with the column. These are the minimum sizes that we need to provide. However, this is the minimum height, and we can easily calculate the required height by dividing the span by 10. When we say span, it's açıklık in Turkish. It's the distance, lateral distance between two columns. You can think it as the length of a beam. So we know this span, this length, this distance between two columns, and in order to find the required height, we need to divide this size into 10. So if it's 6 meters, the span is 6 meters between two columns, the minimum height that we should provide is 60 centimeters for the beam. And that size, that thickness cannot be smaller than 25 centimeters. Uh, when we place the beam, it will be connected with the floor surface, floor body, and all the loads that a floor surface has will be transmitted to the upper side of the beam. So there will be this load distributed alongside the upper side of the beam. And since it will be supported with columns on each end, there will be some opposite forces like that. So with the increasing loads, it starts to bend, it starts to deform into this shape, it bends. And when we take a closer look, the upper side of the beam, the molecules are pushed towards each other like this, and they are compressed. That's where the compression stress occurs. However, the lower part, it's different. This time, molecules uh, are forced to go away from each other, apart from each other, and they are pulled away. That's where tension stress occurs, like that. And we know that concrete is a very strong material against compression stress. So wherever there is compression, we need concrete. It will hold better against compression stress. However, it's weak against tension stress. It starts to be break into pieces again when there's tension. And we know that steel is a material strong against tension. It works for the tension. However, it's weaker against compression. So whenever we have compression, wherever we have compression, we can provide concrete, and where there's tension, we can provide steel reinforcement bars, like this beam. Just imagine you place a very heavy object over the beam, and it starts to bend, and it starts to be deformed, break into pieces, because the concrete holds against, it works against the compression stress, but it's weak on the tension stress. Like that, this is something that we need to avoid. And if we place reinforcement bars where tension occurs, towards the lower surface of the beam, then it will hold. It won't break into pieces. That's something that we need to consider. Uh, the beams and the columns, they can be connected to each other in several different ways. Uh, First, we can provide a no fixed connection at these points where a beam meets with the column. No fixed connection. We can create all these pieces or components in a factory and we can transport them to the construction site and we can just lay the beam over the columns and that's all. No fixed connection. And when we apply the loads, when the loads of the floor are transmitted to the upper side of the beam, the middle part will go downwards and the edges will raise upwards. So it will be deformed like that. It will bend. And in the upper part, we get compression. And in the lower part, we get tension. So our bar, reinforcement bar, will be in this position where tension occurs. And the upper part will be filled with concrete. However, if we need, instead of no fixed connection, we will have a fixed connection in these points where the columns are meeting the beams, like this. And we can provide that fixed connection by tying all the bars of the beams with the bars of the columns. And when we pour the concrete, one object will be created here. There is no separation. And when we apply the same loads from the floor, again, the middle part will bend downwards and we will experience compression in these upper side of the beam and tension in the lower side of the beam. However, since the connections are fixed and since there are columns creating this opposite force, but this time upwards in the opposite direction, these parts of the beams will bend in the opposite direction. Here, this time the lower part will be compressed and the upper part, there will be tension. So we need a different spatial type of reinforcement bars, which needs to follow where the tension occurs. So here, along around this connection, fixed connection, the tension in the upper is in the upper side. So our bar starts here, and then this middle part, the tension will change position. It will be in the lower side. So our bar follows where tension goes and lets the concrete to feel where compression is. And then since there is another column here, again, the tension will be upper side, in the upper side. So our bar needs to be bent one more time so that it will follow the tension and let the compression part to the concrete, and it goes like that. And this is called a bent bar, pilye in Turkish, like that. Again, as you can see here, we have these horizontal long bars in the lower part and pilye or bent bar here where it meets with the columns and these etriye that holds them all together alongside the beam. But this pilye, that's special for beams. And we can create all these reinforced concrete components, floor, body, beams, shear walls, and columns right on the site, or we can create them in a factory and then transport them to the site. Let's take a look where we can do the structure, construct the structure on site. That's what we call yerinde yapım, şantiyede yapım. So First, the workers create these molds and place the reinforcement bars, and then they fill the concrete, they smooth the surface, all the bars are embedded, they create this vibration, and they let time pass. So after the final set, they can remove the molds. And this is a very nice animation uh, that shows the whole structure step by step. So they first creating the columns. They put the bars and the molds, and they pour the concrete in them. After that, they move both the floor and the as you can see, there are well, the right down for us they continue the columns in the upper floor. That we call the upper floor. Here we have the workers putting concrete floor structure, and it goes like that. Or instead of constructing the whole structure right on the site, we can construct them previously in a factory and transport all the pieces, all the columns, beams, even shear walls to the construction site and connect them like that. And that's what we call prefabrike or ön yapım.
This method is called modular construction. It saves time and reduces mess on site. Workers stay on top to guide the pieces safely. Once everything is locked in place, a full house structure is ready, including the roof.
Now, let's take a look at how we can construct floors out of reinforced concrete. Floor is one of our building elements, so it will function to execute certain things for the user. First of all, it will provide a horizontal surface where we can live in. These are livable areas for us where we can stand and where we can put our furniture and have a space. And all the loads will be transferred and met by the floor body first, and then they will be transferred to the beams and then the columns. And these floors, these elements will provide boundary for the spaces. Here in the upper part, there will be a closed space, and in the lower part, there will be another closed space. And these floors will provide separation between these two neighboring space. And if required, if necessary, they can provide insulation, like the sound insulation. Let's imagine the user in the upper side of the floor in the upstairs, they are making music, and there is someone else in downstairs who wants to sleep or work. So if we design this element in a good way, if we make good decisions, then it will provide insulation. It won't let the sound waves to pass from one space to the other one. Uh, and there can be certain components uh, for this element as well. Generally, we create them as layers like that. So here we have the body, floor body, or we can say floor structure. But we need to be careful here because the previous one was building structure. It is an element. This time we are talking about a component of another element, the floor element, and one of its components, it's the floor structure. The building structure will keep the whole building's form intact, and the building structure will carry all the loads. And this floor structure, this component, will hold, keep the form of the floor, that element intact, and it will carry all the loads that are imposed on the surface of the floor. And if we want, we can cover the upper part, which we call another component, a floor covering. We can provide insulations against water, noise, or heat transfer. And if we want, we can cover the ceiling of the lower space, the downstairs space, uh, with this other component. And all when we gather all these components together, that's our element, the floor element. And for the floor structure, for the body part, again, we can prefer timber material pieces that are shaped out of steel or iron metals, different metals, or we can mix again concrete with these steel pieces and have a reinforced concrete floor body. As we apply the loads, just like the beams, the floor will bend like that because the sides are supported with the beams, so they are strong. But the middle part, it's just a thickness, a thin slab, unsupported. So it will start to bend as we apply more and more loads. And we need to design our floor body so that it will hold all the loads. It won't collapse down, it won't break into pieces like that. We can have different shapes. It's not necessarily have to be in this rectangular prism. But in order to have a nice living area, we mostly prefer either a thin slab, a thin plaque, either in the shape of rectangle, like this. So for a rectangle, we know that this side is shorter than the other side, like that, at least half of it, shorter than the half of it. And on this type of floors, on rectangle-shaped floors, the load will be mostly distributed and carried by the beams under the long sides. So the load will be distributed towards the longer sides and will be transferred to the beams under these long sides. That's why we call it a one-way slab, hurdi in Turkish. Please pay attention to this hat. It's not I letter, it has this hat, and you need to pronounce it a little bit longer, hurdi. Or we can have this square shape where the sides are almost equal to each other or equal to each other. And when we apply the loads, we see that they are distributed evenly on all four sides towards these two different directions. That's why we call it two-way slab. The loads will be transferred to the to this direction and to the opposite direction, to the perpendicular direction in two ways. That's what we call it that. And in Turkish, it's called dal. It's not dal. You need to pronounce it softly. That's why we have again the hat. Dal. Dal döşeme. Hurdi döşeme, dal döşeme. And we can create floors right on top of columns without using any beams. Or we can have columns, beams, and floors made out of reinforced concrete all together. Slabs with beams. Let's take a look at the version without the beams. Kirişsiz betonarme plak döşeme. Reinforced concrete flat slabs without beams. As you can see, no beams. The columns are directly tied to the floor. And here we can have a span with maximum 7 meters. As you remember, span is the distance between two columns in this direction and in that direction. So that cannot exceed 7 meters in this type of floor. Otherwise, this it will be so thin and it can break down into pieces under the loads. And the slab thickness, that's important. This thickness of the slab, it needs to be minimum 10 centimeters. However, the upper side, when we apply the loads, when we step on the floor, when we put our furniture and everything, in the upper surface, the load will be spread. But in the lower part, where it meets with the column, the whole force in the opposite direction will be gathered, focused at a central point. So there will be a difference of balance between the load distribution. So there is this risk of punching. That's something we need to be careful about. And in order to avoid punching, the slab thickness needs to be proportional to the span. And we can find the minimum required thickness. That's the minimum size. But as we enlarge the span up to 7 meters, we need to have a thicker slab. And we can find the required thickness by dividing the span into 33. And the area which is not supported by, it's miswritten, not the beams, but the columns. It needs to be columns, so that's wrong. It needs to be columns, must be smaller than 25 square meters. So this part will be supported with that column, that part will be supported with that column, and all these corners will be supported. And there is this unsupported middle area. So this area cannot be larger than 25 square meters. Otherwise, there's this risk of punching. Here in this photo, we realize that there used to be a floor surface which has been punched downwards, and it looks like it's a swimming pool, probably because of the weight of all the water. And since there are no beams, the whole floor collapsed down. And in order to avoid that risk, we can have this transition between the columns and the floor plank, floor slab. Here we can have these drop panels, larger area, and capitals, these parts, so that it will be an easier transition. Or instead of flat slabs, which we should never prefer where there is risk of earthquake, we should never prefer this type of flooring. We should always prefer flat slabs with beams. Here, maybe it will be good for us to summarize what we have learned here on this slide. So, if there is no risk of earthquake, then we can have this slabs without beams. And in order to remember everything that we need to keep in mind, we can have this summary. The minimum thickness for the flat slab can be 10 centimeters, and it shouldn't exceed 15 centimeters. And the maximum span in two directions cannot exceed 7 meters. And please always keep in mind that there's this risk of punching. So instead of slabs without beams, we can prefer slabs with beams when there is the risk of earthquake. So it's like that. The columns are tied together with beams, and the floor slab is cast uh, uh, as an integrated uh, whole object with the beams. So everything is tied together with the reinforcement bars and concrete. The beams and the floor are cast together. And it will be better not just to support the floor slab, but to support the columns and to prevent them to be separated from each other, like this chair. When we apply lots of loads over the chair, there's this risk of separation under the pressure. However, if we prefer beams, that will tie the columns together. So when there is earthquake risk, always we need to prefer slab, reinforced concrete slabs with beams. And there can be, again, different types of connections. The first one can be unstrained uh, 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 type. We have no fixed connection if we want. And that's what we call serbest oturan döşeme, unstrained bearing, between the upper surface of the beams and the floor panels. Again, we can have these precast panels, precast systems, and we can transport them to the construction site. First, we place the beams, and over the beams, we can just lay the floor panels next to each other without a fixed connection. And when we apply the loads over the surface of the floor, uh, like the beams, again, it will bend downwards like this, and the ends where the beams, upper surface of the beams and the lower surface of the floors meet, they will raise upwards, and it will bend like that. And same principle can be applied here. Where there's compression, we need concrete. Where there's tension, we need reinforcement bars. So we need to place reinforcement bars like this in this type of unstrained bearing between the floor surface, floor body, and beams. Or we can fix them where we can pour the beams and the floor all together at once. And we can have same reinforcement bars connected to each other. There will be a fixed bearing like that between the reinforcement bars of the beams and the reinforcement bars of the floor body. Ankastre birleşim. When we apply the loads over the floor body, the middle part will bend downwards, but since the fixed connection between the surface of the beams and the floor, there will be an opposite force towards upwards so that those parts of the floor will bend in the opposite direction, like this. So in the middle, we have compression in the upper part, tension in the lower part. However, with this connection with the beams, the compression will occur in the lower part and there will be tension in the upper part. So again, we need bent bars to follow where the tension is. So it starts here and move towards the lower part. And then if there is one more beam, again, it needs to go upwards. Or we can have a cantilevered floor. As you can see here, there is no support on this end. That's what we call konsol in Turkish, konsol döşeme. And it's supported only on one side with the beams. It's connected, fixed, connected with only one side, like this balcony. It has no supports in three sides, only one side is supported with beams and structural system, like that. When we apply the loads, it will start to bend in a different shape. So there is a limit. And if the loads exceed that limit, they will collapse. The whole floor surface will collapse down. And the deformation is something like this. It bends like that. And when we take a closer look, we see that the lower part is being compressed and there's tension in the upper part. So we need to place the reinforcement bar in the upper level this time, like that. Slabs with beams, kirişli betonarme plak döşeme, like this. And the maximum span that we can have in this or that direction, it's 6 or 6.5 meters. It shouldn't be more than that. The slab thickness can be minimum 10 centimeters. It shouldn't be lower than that. And maximum 15 centimeters. It shouldn't be thicker than that. But what if we need bigger spans? Of course, we need to increase the slab thickness. However, if the slab gets thicker than 15 centimeters, it will become heavier and heavier. That's something that we don't want. We don't want a heavy load over the beams and the columns. And it will become more expensive. So instead of thickening the slab more than 15 centimeters, we can have supporter smaller beams. Here, these are the main beams, ana kiriş, which connects the columns and supports the whole loads of the floor. And we can have smaller beams, which we call girders, ara kiriş, so that without increasing the thickness of the slab, we will support the loads. First, the floor body will get all the loads, and then it transfers the loads to girders, and the girders will transfer the loads to the beams, and the beams will transfer the loads to the columns. They are called dish or nervür in Turkish as well. Ana kiriş main beams, girders, ara kiriş smaller beams, dish, nervür. And let's summarize all these information here. Maximum span can be 6.5 meters. Again, it has been miswritten here, not 7 meters, 6 or 6.5 meters. And the thickness can be 10, minimum 10 centimeters, maximum 15 centimeters. But what if we want to enlarge the span more than 6.5 meters in both directions? Then we can have girders. And if it's a rectangular shaped floor, which we call one-way slab, then we can have girders parallel to the shorter side so that the loads can be distributed to the main beams on the longer sides, like this. Columns are connected to each other with main beams, bigger beams, and the girders are parallel to the short side to transfer the loads to the beams on the longer sides. One-way joist slab, or if we are designing a square-shaped two-way slab, then we can have girders in both directions like that, in both this direction and that direction, so that they will transfer their loads to the main beams and then the columns. That's what we call a waffle slab. Let's examine one-way joist slab. That's what we call a ribbed slab, in Turkish boşluklu dişli döşeme or nervürlü döşeme, where we create a series of girders and there is void, there is empty spaces between these girders. And it looks like that. Let's have a section. Let's imagine that we are cutting through this line. That's what we get. We cut the girders and the floor slab, and there is nothing in between, just an empty void. So the maximum span can be 5 meters in this direction, that will be the short side, and 12 meters, up to 12 meters in this direction, that will be the long side. These are the maximum sizes. And the slab thickness, that thickness here, this one, that thickness can be decreased down to 5 centimeters because this whole slab is supported with girders. it doesn't need to be minimum 10 centimeters anymore. It can be down to 5 centimeters. That's the limit. And the girder thickness, this distance for each girder, that one, that size, it needs to be minimum 10 centimeters. And the distance between two girders is distance, the size of the void, that one, can be minimum 40 centimeters, maximum 70 centimeters. And that's what we see since they're all empty. There are voids between the girders. This is what we will see. Sometimes it can be nice to look at to a ceiling like that, but sometimes, some other times, we want a surface, a full flat surface for a ceiling in downstairs space. So we can use certain pieces to fill up the voids between girders. That's what we call filler joist slab, ribbon block slab, or asmolen döşeme in Turkish. And these pieces can be created out of clay. We place them here so that the whole void will be filled. And when we apply the ceiling covering, we will only have one thick floor with a flat surface for the ceiling. Or instead of clay, we can have AAC. That's a material which we call autoclaved aerated concrete. In Turkish, it's gazbeton. Or we can have pieces made out of pumice, beams in Turkish. That's a natural stone, pomza taşı. Or we can have a lighter piece which is made out of plastic, extruded polystyrene, EPS. But please do not forget, again, where there is risk of earthquake, we shouldn't prefer that type of flooring because it is heavy. It's heavy and we don't want a heavy load over our columns and beams. So, and it's thick and it's not flexible enough. So, we shouldn't prefer that when there is a risk of earthquake. Polystyrene, polystyrene, there are two words here. Strand is the type of the plastic substance, and poly. So this is one single strand uh, molecule. As you can see, there is the special bond between these atoms, carbon and hydrogen and something. And that's what we call a monomer, a single molecule of strand. And in order to create this better material, we need to multiply this monomer and create a chain of monomers, which we call a polymer now. That's the reaction that we call polymerization. As you know, poly means multiple. So we create this chain of strand monomers. It's now a polymer. That's why we call it polystyrene. And that's this substance that you are very familiar of. And when we take a closer look, we see these bubbles because each one of these monomers are heated so that they expand. That's why we call expanded polystyrene, EPS. But if you don't want these bubbly loop, these different particles, and they are in order to create these boards, they are all gathered up and glued to each other, and forms or molds are needed. So instead of expansion process, we can change the procedure, and in order to create these uh, full body, we can, instead of expansion, we can have extrusion, which means that half liquid plastic substance are forced to go inside this little gap. and extruded in this way. And we don't have any bubbles, but a full solid, uh, more condensed uh, material. Same polystrate. This is expanded. This is extruded, and it's called XPS this time. Not EPFs, but XPS, extruded polystyrene, and that's called EPS, expanded polystyrene. Uh, and we can have these filler blocks with EPS or XPS, so they will be lighter. So let's take a look at how the filler joist slab and ribbon block slab is created. So they constitute the columns, and when they place these molds, these are horizontal timber panels, and they need to be supported with scaffolding below. So first they lay these filler blocks, ANCs or clay or EPAs or other substances next to each other, and you can see there are little gaps in between. When they pour the concrete, those gaps will create the girders. And here, the columns will be connected with each other with main beams on the sides and in the middle. So the whole floor will be supported with main beams, and it will be supported with girders. And once they lay all these filler blocks, they start to do the reinforcement bars. Like this, and you see the band bar here, and the little bars is here. That's one of the main beams. And then on the other side, and there's another main beam. They are going to place the reinforcement bars for the girders and the floor slab as well, and they are going to tie everything up to each other. Let's move on. We don't need to watch it one more time. Once all the reinforcement bars are set, they will pour the concrete, and as it sets, they will take out the molds, and this is what it will look like from downstairs. These are the filler blocks next to each other, and it's all embedded in the concrete. So let's take a look at the distances and sizes that we need to provide. First of all, uh, we need to select one of the filler blocks. Let's imagine that we selected these blocks, and it has this, one of them has this piece as these sizes. This is 20 centimeters, that's 40 centimeters, and the height, there are different options. If we want, we can prefer 20 centimeters or 25.75 centimeters or 30 centimeters. Let's imagine that we prefer the 30 centimeter version. So whenever we have this section, when we cut through here, that's what we see. First, we are cutting through the reinforced concrete floor slab and girders, and we are cutting through these filler blocks. And the maximum span that we can have in this direction, in the short side, again, it's 5 meters, and in the longer side, it can be up to 12 meters, no longer. It shouldn't be longer than 12 meters. And the concrete thickness, this thickness of the slab can be minimum 5 centimeters. Girder thickness, again, it needs to be minimum 10 centimeters. And the distance between the girders, in the previous version, it was between 40 to up to 70 centimeters. However, this time it depends on the filler block, this piece. If you prefer that, that's 40 centimeters. And the thickness of the whole slab, that distance, the whole thickness. Again, it depends on the height of the piece. If you prefer 30 centimeters, we need to add 5 centimeters for the concrete thickness, slab thickness. So in total, it will be 35 centimeters. For one-way joist slab, either filled or unfilled, it doesn't matter. The maximum distance in this direction is 5 meters. Maximum distance in this direction, it's 12 meters. Let's take a look at the waffle slab. That's the last one of our floor types. And it's called kaset döşeme because from downstairs, it looks like a waffle. Kaset is called these square voids in between the girders, and they are created with a special type of form, made generally out of plastic this time. So let's take a look. With the vibration. And because of its shape, the girders will transfer the loads in two directions. That's why we call it two-way slab. Let's have a section here. So we cut through the girders and the floor slab here. Maximum span in this and that direction can be 16 meters, no more than 16 meters. The concrete thickness, that thickness can be minimum again 5 centimeters. Girder thickness, that distance can be 10 centimeters, and the distance between girders, they depend on the form. Uh, there can be different forms created with different brands. So we need to first prefer or choose one of the forms, and according to the distance here, our waffle voids will be created. And the thickness of the slab, again, will depend on the form. It's this height plus 5 centimeters for the concrete slab thickness. So let's put these to our summary. So that's the end of it. We can use this page whenever we need to remember all these measurements. So it's like the summary. It can either be flat slabs without beams, but we shouldn't prefer them when there is earthquake risk. We should always prefer this type of flooring. And if we want to enlarge the span, we can either have one-way joist without the filler blocks or with the floor blocks. But again, we don't want a heavy floor, so that filler block type shouldn't be preferred when there is earthquake risk. And the maximum span that we can provide is a two-way waffle slab with 16 meters. So keep this slide in front of you all the time. So whenever you need these distances, you can take a look. And that's the end of our video for today. Next time when we meet, we are going to talk about what are the other material options apart from reinforced concrete for the building structure, and how we can design or make decisions, correct decisions for the structure, and how we can express our decisions in a right way so the builders and related people can understand our decisions. Okay, thank you for listening. See you next time, hopefully.